engineering direction.
Yes, yes. Good afternoon. It's still morning here, so good afternoon to you all. Thank you very much, Slava, for your wonderful introduction. Yes, we go back many years now, and we've been working together for quite a long while, and with a lot of success, we could say, as well. And it's been a pleasure working with Vyacheslav and his team, and I hope I don't embarrass you, Slava, now that I'm going to give something, a talk, and I hope I don't waste your time. So if you think it's too much nonsense, please tell me. I will stop immediately. Shall I start?
Yeah.
Oh, okay. I'm not a very conversant Zoom user, so I'm just trying to share my screen can you see my screen now?
Yes, it's switch on.
Yes.
Good.
Okay. So I've prepared around a 25 minutes talk about the digital transformation of industrial systems. Basically, this is the transformation to Industry 4 in another word. I've put a picture of the mini factory, the BMW, which is now owned by BMW. I visited the factory about on 24th of October. Oh, sorry, it jumped. And as you can see, they are moving to Industry 4 with a major investment in the next 5-6 years. And they are going to basically change all their production system to smart systems and Industry 4.0 compliant. So, the challenges, the modern challenges when we go out and when we discuss with industry and the research councils who pay most of the money for research, the challenges that they pose us and they want us to deal with is to build machines and processes that produce no defects. Build machines and processes that never suddenly fail. So zero sudden breakdown. Not only they electromechanically do not fail during the production process, but they are also immune to cyber attack. Build plants that always work at their expected capability and capacity in an ever-changing environment. Build plants that emit minimum greenhouse gas emissions, zero carbon, and design processes which can create the knowledge and know-how to facilitate circularity of resources. So in the wider context of circular economy. So as you see, we are shifting from, as engineers, make things that work properly, perfectly, the quality to maintain as long as possible at cheapest price. We have much more bigger challenges now. So in my sort of interpretation, if we look at the evolution of industry from what we call the origins of industrial revolution in the early to mid 19th century, we had the foundations or the basis of engineering disciplines who had overall direction and created job shop, highly skilled, make-to-order products. All those old workshops, oh sorry, suddenly this Zoom jumps, but so from there, in the mid 20th century, early 20th century, mass production came to the fore through Henry Ford as one of the major pioneers of mass production, standardization, machine tools, serialization, bringing down the skill level so that the production cost becomes lower. That was where the dominance of management science and operations research created tools and techniques of optimizing, line balancing, flow management, etc., etc. And then finally, later in the 50s and 60s, the advent of robotics, automation, and passive adaptive control, mechatronics and control science sort of took the lead and brought us to Industry 3, which is mainly a highly automated adaptive industry, passive. So basically it is capable of taking sensors and understanding, but quite rugged and not intelligent enough. And then at the turn of the century, we have shifted to Industry 4.0. Actually, I need to show off a little bit here. I wrote the new paper, the modern white paper for Industry 4.0 for the European Commission as the lead scientist in it. So in that definition, we described Industry 4.0 as, with the advent and the buildup of advanced ICT capabilities, information and communication technology, machine learning, artificial intelligence, we have created smarter systems. These smarter systems are active learners. So basically, they have a wider range of data acquisition. There are capabilities to widen up our observations, so big data. Aggressive prediction. So these are systems that not only wait for something to happen in their environment to react, actively predict what is going to happen in their environment, so they make the preparations and adjustments ahead of time. They govern complexity. So these are now, we are dealing with much more complex systems. Systems now, whether they are manufacturing systems, artifacts, economical systems or socio-economic systems, political economic systems. These complexity is bringing the cross-sectorial multidisciplinarity into it. And cyber-physical systems are good examples. Smart material, complex designs, combination of functions, and operations that was not possible many years ago, now is becoming possible. So with this continuous learning and continuous and aggressive prediction, and this complexity and capability, we have this provision of continuous optimization, localized optimization, and now because of the Internet of Things, we can have global optimizations. So we can connect not only one component to another component in a machine, but also connect machines to machines, processes, then factories to factories, and then factories from different regions in different countries. So this digital revolution of industrial systems, we go back to the classical systems approach, how we turn this into this system is basically what we have done the last 40, 50 years. So we have the full life cycle of systems engineering, where you have the plant, you have the data acquisition capabilities, which is called sensors and actuation. We have the capabilities of data analytics. So we have these data points, they have these signals. We put them together in a format that then it can be translated into mathematical representations, symbolic and mathematical representations. So we translate the physical system into a digital system. And the closer and more accurate this representation is, thanks to this capability, we can have a good representation of system state. Once we develop it, we test and validate it, improve it if it requires, then we come with decision making. And that decision making is that how can I improve and optimize or retain or maintain the current optimal levels? If I fall below optimal level, what do we do? So now we're talking about, this is still the old system. But what has happened now, this new evolution, thanks to the capabilities of Internet of Things and the sensor technologies, availability of sensor technologies, and high computational power, we are now discussing that our simulation models turn into digital clones or digital twins. These digital twins are the digital representation of the physical model in real time and predictive format. Basically, why we create a digital twin is that it gives us a better visualization, better dissemination, so we can now use multiple people from around the world to give their views and knowledge into it. And more importantly, because the system is connected to the physical world, it basically evolves, ages, and changes with the plant. So once you have the digital twin, you can now implement ideas, new ideas, without disturbing the real system. I should tell you, in the last 10 years, I have been working with some of the world's most advanced plants in all sectors, from automotive to heavy metal to advanced composite metal industries, to process plants, from wastewater plant treatments to water plant treatments to biorefineries and oil and gas. We are still a long way to go, but we are in the right pathway. And it's good for all us systems engineers and control engineers. This is the best time for us to reap the benefits and, in other words, make good money out of these evolution. So, what is the modus operandi? How do we put this into practice? In my own systems engineering research group, we use two methods, two mechanisms. One mechanism is the traditional mathematical modeling route, which is quite, well, not quite, is very, very helpful, very much equations, transfer functions, neural networks, a lot of inferential, physical, and heuristic models that are collect the information, use the historical data to represent the system. However, in many of these cases, in my own research, I realized that these models are not sufficient. Even if we're accurate, we're not timely. And time is crucial for most of our systems nowadays. We don't have historical information. We don't have capabilities to have those historical information. Our system reads fast response, quick processes. I want to make plastic bottles that passes my molding machine, injection molding machine, at 200 per minute. So a neural network model, you tell me whether it works or not. In my experience, I have tried, it doesn't. So we need something better. So we suggested in the paper in 2013 something called event tracking. So real-time data acquisition and digital modeling. In this method, we collect unbiased, we open the system to infinite number of data acquisition points, sensors and actuations, and read the data. So if you see in this example, we have a blue line, a green, and a red. These are the sensor values and sensitivity index of a specific output to 3 known inputs. And as you see, as the time passes, the sensitivity of that parameter, output parameter, stabilizes. So I can now declare that sensor green and sensor red have high relation to this specific component output, and sensor blue has no impact. We use this technique and mechanism to group sensors and actuators together. From that, we create state classifications. We create the genomics of process. And this genomics of process creates the DNA of operations. At the end, we come up with lookup solutions. So very quickly, we can go back to the system and adjust and adapt. This is all digital. It's an engineering. For the first time, we're using models that do not use any maths for control and optimization. However, this is good, but not extremely scientifically accurate at times. What we do, we connect these two together. So, sorry. So, once we connect these two together, we can optimize and improve the models, the classical models, bring in new parameters, variables, change the correlations, update the models, but also use the same models to update the system boundaries and transitions and continuity and continuums for the digital solution. So now we combine these two for optimal processes. This can always work in the back end, and this works in the front end. So two parallel systems. So the questions, sorry, I've lost track of time. So please let me know if whenever I'm exceeding the time, I will try to shorten the. So the questions that we need to answer in this transformation process, we have 4 clear steps. Is the data that I am collecting, the information that I am receiving, is it good? Is it validated? Can I be sure that it represents the state of the system? The next thing is that once I take this information and approve that the signals are correct, then what do they represent? What do they show? From there, how can I translate this into a model that the brain can then, to bring intelligence to it? How accurate are my models? Does a physical model possible to be made? Do I have to use statistical inference models? Or I have to use heuristic models? Or a combination? And how good are they? How representative are they? And finally, what are my objective functions? What do I want to control? Do I want to reduce the energy consumption? Do I want to reduce the cost of operation? Do I want to increase productivity? Do I want to increase efficiency? Do I want to increase sustainability? Or a combination of them? So multi-objective or single objective functions. And then how do I update my system? So each of those poses a specific problem. The first one, so these are just some examples that we are using to address some of those problems. So one of the problems is loss of signals, loss of data due to wireless communications, poor communications, low cost or low quality sensors. So traditionally, Kalman filters were used to estimate the errors and find ways to compensate for their errors. So we have worked a lot on improving and coming with methods and techniques. One of them that we have just recently nearly published, so we've just submitted the minor corrections. The protocol-based Tobit-Kalman filters. And the idea there is that we estimate and compensate errors for considering low-cost sensors, cheap sensors, and volatile wireless communications. The application of this is in our, we have a number of projects on building smart farming solutions, highly industrial smart farming solutions, but low price. So we have systems that only cost 400, 500 euros that collect information from the farm and transmit this information and use very cheap material. But you lose a lot of signals. So that was the reason that we had to do this. And another project that we did with Vyacheslav, which is very exciting, is using X-ray and optical images to evaluate the quality and security of electronics and microelectronic devices. In this technique, we fuse two, so when one or a single sensor or one type of sensor is not good enough, we can fuse multiple sensors to give us better representation of data. I call this the Superman system. Basically, the reason that Superman is, one of the reasons that Superman is Superman is because he has X-ray vision. So in order for you to look at the quality or whether there's a tampering or there's a mistake in a specific circuit, traditionally we use optical imaging. So visual surface, we look, we detect, and we approve or disapprove. X-ray systems look through as well. So you can fuse these two together and get a much better representation of a system, even better than human. So in this way, we can detect the differences, the changes, the loss of quality, etc., etc. The other problem of sensors, data acquisition, is sensor technology itself. So on another series of projects in water industry specifically and wastewater treatment, we are asked to reduce the energy consumption and the nitrogen oxide or the greenhouse gas emissions of these plants. In Europe, EU, 6% of the energy consumption is for treating water and wastewater. It's billions. So anything that reduces that is highly desirable, and they're spending millions on our research to do something like that. So one of the ways that you can control the greenhouse gas emission and energy consumption is to see or to monitor the emissions of nitrogen oxide. But in order to do that, a classical gas analyzer from ABB or another German company that we work with two companies that we work with, costs $150,000 pounds. One system. Not many water treatment plants can afford something like this. So we are now introducing soft sensors. What does that mean? That means that we use the very expensive system and a few representative plants. We find the relationship, the correlation between nitrogen oxide emission and other sensed and actuation knowledge and parameters that we have. So like CO2 emission, energy consumption, flow of material, volume of the material, the oxidation process, and out of that, we find the relationship with nitrogen oxide. So we create an indirect sensor technology. So we make predicting nitrogen oxide emissions using self-sensors for the places that cannot afford expensive sensors. And finally, another challenge on data acquisition is that now people want, or companies want, their machines not to make any defective products anymore, or they do not break down during the production process. So the only way to really be able to achieve this is continuous online monitoring of the health of the material and the health of your machines. So we are introducing new mechanisms, new techniques to add to the knowledge: sensing, hearing, smelling, seeing, touching, all the senses. We are now adding, we're making these machines much more clever with these data acquisition points. The next challenge of data acquisition is, after data acquisition, is systems modeling and simulation. Here, I don't talk about the traditional modeling. I talk about more about the data-driven modeling nowadays that we are working on. So deep learning, neural networks are being used nowadays to create new models, new analytical models, new numerical models, and they're working very well. However, as I explained previously, a lot of these solutions do not necessarily provide a timely or accurate response solutions. We have seen this in detecting or evaluating laptops in a fast-moving security system in the airports. I have seen this working with Bosch for autonomous vehicle driving. We need a much more complex system, or a much more faster condition situation awareness mechanisms and decision making. In aviation industry, also we have done some work on how to reduce the response time of a specific maneuver, and in factories as well. So one example I can give you about our image analysis on electronic devices and security systems, we couldn't use the traditional image processing techniques. So we came up with a new solution called entropic gray imaging to speed up the process of detection and evaluation. And we compared, in comparison to one of the most commonly used techniques, which is histogram by oriented gradients and support vector machines, the combination of these two. In comparison to our EGI, we have realized, although we lose 0.8% accuracy, but the speed of our work is 40 times faster than Hagen SVM. Imagine for this sort of queue. My first estimation, I gave a presentation for security in London, airport and aviation security conference, that in the 30 largest airports in the world, if we deploy our technique for automated detection, so basically you not only have less pressure on operators because it becomes automatic, we will save 400,000 hours of operational time. A huge achievement. On aircrafts, again, we used our event tracking against entropy-based sensitivity analysis, which is one of the most common or the most suitable method for real-time situation awareness analysis or sensitivity analysis. And our system responded to the aircraft maneuvering in 5 milliseconds, whilst the entropy-based took 300 milliseconds. So you can see the speed of reaction in high systems. Sorry, how much time have I got?
How much time do you want?
Well, I think I have about 17 slides. So I just got to slide 9. But if you tell me what is my limit, I will keep it to that. Shall I continue?
Yeah, I guess 10 or 15 more minutes.
10 or 15 minutes, yes, okay. 10 minutes. So, some more examples of discrete and continuous systems monitoring. So, one of the projects that we have, 3 projects, European Horizon 2020 projects, is about zero defect manufacturing. That means we are building systems now that we ensure that there are no defects during the production process. Through that project, we just recently finished one of those projects called Z Factor. This is the logo, Z Factor. We have defined what we call the genomics of production process. We have now created DNAs, genes that create defective products and genes that create optimal products. We are now deploying this in a number of large companies, one of them Microchip, which is a well-known global company, and they produce micro semiconductors. And we do one with hard metallic composite manufacturers as well. Do it. However, it is very important that we say, oh, okay, we can spend hundreds of hours on quality and make sure that we don't make any mistakes. But this is not a real production system. In a real production system, you have to balance between a number of key performance factors. We have defined 5 key performance factors: quality, productivity, which is all related to overall equipment effectiveness and efficiency, energy consumption, environmental impact, which is greenhouse gas emissions, and inventory management. So basically control and monitoring your feeding of the lines. These were the critical key performance indicators that we had to optimize the performance of the system ourselves. And we used, we created these models, the transfer functions. We collected real-time information from the plants. It went into our system's big data collider, event tracking and event modeling. We extracted the models, the transfer functions for these key performance factors. We generated quality loss functions and cost functions. And from there, we developed a decision support system and called it the green scheduler. So we come with the optimal process plan to maximize the performance of the system. And we don't only just send a schedule, because there are a lot of schedulers out there. We don't just do a beautiful mathematical solution, but before we implement it down into the plant, we use a process simulation, discrete event simulation, to validate and verify the optimal schedule. If it is verified, then the control commands go down to the system. This turns into a fully autonomous and smart Industry 4.0 production system. In another project, we were asked to build a system, a machine that ensures it will never fail, a process that will never fail during the production line. So one of our key industrial partners in this project was a company that produces plastic packaging for food industry. It's very interesting, this Italian company, when we were discussing the project, I told them, I want to help you to build a machine that will never fail. He said, oh, this is impossible, and so on and so forth. And he said, you know, when my machine fails in Coca-Cola, for example, or in pharmaceutical, 1 hour of my machine being down costs the manufacturer $5 million an hour. So you can imagine the value of building a system that you can guarantee that it will never fail. So one of the machines that we worked with was a compression molding machine. They make 200 caps per minute. You can't see the speed of operation. It's so fast. So we had to monitor. This machine has 144 sensors to monitor every single bit of mechanical, hydraulic, and electrical sanity of the machines. So we built a system that totally and fully predicts the remaining useful life of every machine in its own operational environment, and provide a decision support system on how to deal with that remaining useful life or the predicted breakdown. In another project, we use similar techniques, but in a totally different environment. This is in water plants. Here, we are dealing with biological processes. But yet again, we are smartifying these systems with the same vision, systems engineering vision, with similar performance indicators or different indicators, but with a very specific objective function, and that is maximizing circularity. I want to preserve, retain, and maintain water. So I want to maximize the circularity of water. In that visit I had, which I had the whole production line due to COVID all to myself. I was the only visitor there, and I walked around the 10-kilometer production line, having full access to the production system. I came to this very interesting sign, which was on a big wall in the BMW factory. And it fascinated me. It says that the competition is changing. Whilst they think BMW believes that this current competitor is Mercedes and Tesla, the new competitions for them are knowledge-based companies. Amazon, Apple, Dyson, and Google. And another big thing, Industry 4.0 is coming, and it's a major shift. And companies like BMW and many others that I'm working with, like Philips, Microchip, they're all going towards this evolution. And not only the advanced manufacturing, automotive and aerospace technologies are going toward, and telecommunication technology is going towards it. But I am now we are trying to push the more traditional water, oil and gas, and more older systems as well, with major challenges, but wonderful opportunities as well. These are some of the indicative applications. If you are interested, I have sent the presentation to share it with you. These are some of the indicator papers of ours. And thank you very much.
Mm-hmm. Thank you very much for your presentation. It was very interesting, very exhilarating. So, if you don't mind, I would like to ask you a few questions.
Yes, of course, of course.
First of all, in your opinion, if the university want to train new system engineers or want to prepare a new system engineer, what should we start with? Should we start with cyber physical systems right away, or we should start with engineering disciplines and then build up on that?
In my view, nowadays the engineering is changing. It's making a major shift. The classical engineering courses are not sufficient anymore. So what I believe is that we need to create new courses which combines principles of mechanical, principles of electronics, some elements of communications, and operations research.
Mm-hmm.
That combination now in different levels. So we can start with the general engineering at the first level, but then go to the more integration, and then specialization in higher years and higher, when we go to the higher years. Now, someone becomes specialized in software, soft robotics, soft automation, soft systems. Some become experts in cyber physical systems. Some become experts in electromechanical systems, and so on and so forth. So, yeah.
But the very first course should be state-of-the-art cyber physical systems, or should be fundamentals of mechanics? Let me.
I think fundamentals of mechanics.
Okay, thank
Still,
you.
we need that, because if we need, because one of the problems, the Americans tried this with industrial engineering in the 50s. So they created these engineering management experts, which fell in between. They were hoping that it will bridge the gap between engineering and management. But the problem was that the emphasis was very much on the operational research side of things. Industrial engineering really went into that. So a lot of industrial engineers don't have the strong electronics and mechanics background to talk to traditional mechanical engineers. So I think we still need the foundations to be there before we start with cyber physical systems.
Thank you very much. And another question I have about this event modeling technique that you studied and that you implemented at several manufacturers. How long will it take to start from the scratch, and how many people resources? Like the very simple minimum viable product.
Sure. So if you imagine, it depends on the complexity of your production system. So depending on if you have, so for example, the type of groups of systems that we worked with, I can say from one extreme is a highly automated Treadsky machine, which basically assembles microchips, and it's fully automated. So this machine does everything like a robot. Ficantech is the same. So you have a machine that has a PLC. It has sensors, vision sensors, and sometimes some of them have vibration sensors, etc., etc. Normally with these, if we have access to the PLC, the source code of the machine, then you will need one good engineer from our side access to that information, and it takes about 2 months to implement. On the other extreme, you have systems which have not many sensors, not many or no sensors. So you have to go in, and for example, in one of our projects is one of the partners that we have. They make tungsten cobalt, which is a hard metal. That they use it for tooling and oil rigs and things like that. They manufacture those. So so they have forming, hot forming, and a lot of processes, and then machining to make these oil rings and things like that. The problem with them is that they don't have many sensors. Most of the work is done by experts. In cases, we add sensors where we can to collect automatic data, but we have also created panels, so experts or the operators will provide observation information. And through that, we collect this information and build our event tracking model. This normally takes up to 6 months.
Thank you very much. And I think there is one raised hand in the chat. If that was no accident, then please ask the question.
Да, спасибо. Hello, thank you for the excellent presentation, Dr. Musavi. Yes, a question for you, sir. you build these zero defect systems. Is there really no defects afterwards, after you build them?
Is there no defects? We are still hoping, but we have brought down the defects. What I can say is that we have, in one of our projects, which was mainly on design of the monitoring system, we can say with near determinism. So we were going to deterministically say that the 10th component that goes in will be defective. So that means we are implementing this. That means I will give, for the time being, my operator ahead of time, exactly near deterministically, from when they will have the defects. And in another project, we are now building the control feedback loop on it. So basically, we are making the machines to respond to these defective genes that are being created. So if it's possible that the current machine to make the adjustment, it will do it. If it doesn't, and the part still remains in the conforming tolerance, the following machine will make corrections to its own. So it will correct that mistake, or does not exacerbate the previous mistake. Or the other thing of operation, if the material has gone beyond correction in downstream, we will put a value to it on recycling, recyclability, and reusability. So immediately I will tell the operator to remove this machine, this part, because if you do more things to it, you will destroy it even more. So the earlier you take it off, you may be able to use it more, or to recycle it, or to remachine it, etc., etc. So yes, not now, but I'm hoping. I want to. Well, otherwise they'll take me to jail, because they're giving me a lot of money to come up with it. But I'm hoping in the next 5-6 years, we not only have a monitoring system that predicts, but also acts accordingly and adjusts the system for zero defect. Yes.
Mm-hmm. Thank you very much. I think that were all questions. And once again, thank you very much for your very interesting presentation. Hope you have a nice day.
Thank you. Thank you very much for inviting me.
Hope to see you next year on the next year conference as well.
With my pleasure. With my pleasure.